I sure hope that's recording. My Zoom window does not want to tell me if it is. There it goes. So yeah, I've made these slides. Please, you can derail me at any point. These slides are for you guys. Okay, so if there's something that I'm not talking about that you want to hear about, we can go there. Totally fine. But here is my best attempt at giving you knowledge for the final. All right, so we have non-programming things and we have programming things that we talked about this semester. So let's start with the non-programming stuff that I don't ever want you to forget. All the very important things that we talked about. I guess if you take nothing else away besides the programming stuff, I want you to take away our ethical theories, because that's a great way to analyze a topic and try and figure out what you think is best. So let's talk about Kantianism and utilitarianism. Kantianism, let's start with our boy Immanuel Kant. First of all, this is a study of ethics. Kantianism is a way, it's a point of view, it's a frame of view. It's a way to look at an ethical question and try to decide what you like about it, if it's a good thing or a bad thing. But ethics in general, remember, that's just the study of like what is right, what is good, what is true, what you should aspire to be, what's worth anything. That's ethics, trying to discover that. And what Kant thought, he was a person, and Kant thought that we should always act in a way, like obey the golden rule. You should act in a way that you'd want everyone else to always act. And so everyone was key, and always was key. Maybe always was the more important word. And the idea there is you should never like lie, or you should never like make any special exceptions for yourself. No special exceptions. Lying is a good example. Kant is totally against lying because he would never want to be lied to, right? What would you want everyone else to always act like? Well, I would not like anyone to lie to me, so maybe that means that I should not lie in general to anyone, ever. So that's what Kant thought. And he had a bunch of different ways of describing what he claimed to be the same things. So like these two bullets are, Kant argued that they were the same thing. We'd have to take a philosophy class to fully understand that. But another thing that he said was we shouldn't be treating people as just a means to an end. We should treat them like human beings that have wants and desires and purposes and things like that. So don't try to just get something out of somebody, because you wouldn't want to be treated like that. You would like to be treated like a human as well. So that's kind of how they come into play with each other. So that's what Kant thought. And he argued that those two ideas were exactly the same, but usually when we were talking about stuff in this class, we were talking about it from the first perspective. Is this thing something that I would want everyone to always do? So that's the question you would ask. And so Kantianism is great to understand, like, what should we do? It does sometimes break down, right? So, for example, lying is a good example of where Kantianism might break down. You would want to lie to some people sometimes. I think we all have, right? To your kids, for example, before they get older or something. So a silly example is like, wouldn't you want to lie to like a murderer who comes to your house and who's looking for your friend and who wants to kill them? Wouldn't you lie and say that your friend like moved to Florida or something? You would totally want to do that, but Kantianism says no. And you'd have to use that in your argument somehow. Like most people would want to lie, but Kant would say no. I would not want anyone else to ever lie to me, so I have to tell the truth to this murderer, and so be it. So that's unfortunate. But technically, murder shouldn't be happening in Kant's world. Maybe this is a bad example, right? The murderer should never want to be murdered, so maybe there should be no murdering. But the world is not like that, I guess. Another example is stealing. Like you can think of some good examples to steal, right? If you have nothing and you need to feed your family, for example, that seems like a very selfless act at that point. You might as well steal. But again, Kant would be absolutely against that. He would rather you starve, because he would not want anything stolen from him. So he would argue that no one should ever steal under any circumstance. And so Kant is very, very rule-based, rule-focused, and that could be the downfall of his ideas if you're using that in an essay. But that's one way to approach a problem and to view it. That's how it's supposed to help you. All right? Any questions about Kantianism? Remember him well? All right. Next was utilitarianism. It was like the flip side of Kantianism. It was able to be bent to our will sometimes. It does not always think the same thing. So utilitarianism, a strong proponent of utilitarianism was John Stuart Mill, though he did not coin the term. He was just a big fan. And utilitarianism is all about utility. There it is in the word. It's maximizing the utility or the happiness or the pleasure that comes out of any action that you're thinking about doing, any ethical question. So you're trying to maximize the utility / happiness for every possible action, and that is you're weighing everything. And you're not weighing your own utility and happiness, you're weighing everybody who could possibly be affected by this decision's utility and happiness. So this is for everyone. So it's kind of selfless for everyone, not just yourself. That's another way to look at a problem. So it's like, all right, you weigh your options. Like I could either do thing X or thing Y, and you try and think about all the good things that could happen if you did thing X, all the good things that could happen if you did thing Y, subtract all the bad things as well. But like if there's more good, then that is what wins out, and that's what you should do if you only had a choice between those two things. So that's what Mill would think, and that's what utilitarianism is all about. It's all about the consequences of an action. Like maybe I need to lie, and I shouldn't usually lie, but I have a really good case for lying right now because the consequences are beneficial to the most amount of people. Something like that. So that's utilitarianism, how it thinks. It's maximizing utility for everyone as a whole, not just you, not just yourself. No exceptions. Kind of like Kantianism in that sense. Though it does break down because sometimes there is, you shouldn't just, some people are more important than others sometimes, things like that. And that could help you in essays as well. But another silly example, right, was like, should you murder one person in order to save 50 people's lives? They would die if you did nothing. Should you go and kill this one person to save 50? Taken at that level, not knowing anything about the people, a utilitarian would be all for killing that person. They would totally want blood on their hands so they could save the 50 other people. But of course, it can break down when that one person is your family and as a family member and the 50 are just complete strangers, when the 50 people are like prisoners that did something horrible and the one person is innocent, stuff like that. You can play with this idea a lot. But in general, utilitarian would be about giving the most utility for the most people. And so they would want to save the 50, even if that meant they had to kill somebody. All right, so that's utilitarianism. It's another way to look at a problem. None of these theories tell you the right answer. It's your job to figure out what you think. But you can use these as firepower to get you started and to start thinking about what you believe is correct. So that's what these theories are all about. We're good with that one? So that's those. We should be pretty comfortable with them by now, I hope. Next we had fallacies. That's another big thing that we talked about, had a very long essay about. A fallacy is a very logical thing. It's a problem with your logic. It's an error in your reasoning or an argument that you're trying to make. So it's like the second you put a fallacy in your argument, or somebody does, that argument becomes incorrect and you cannot trust it. So it's wonderful. You'll see it a lot in colloquial speech, but the second you hear a fallacy, that means that something is wrong. We learned very well that every single kind of fallacy has a name describing what's going wrong in the argument, and we've learned to analyze and pick those apart, which is good. And so just to get us back in the fallacy mode, I found some memes on the internet, and we'll analyze why they have some fallacies in them. So here's a couple funny fallacy meme examples. All right, so this first one is a false dilemma fallacy. And remember that the false dilemma fallacy means that it is, false dichotomy is another name for it. It's like pretending to, or it's trying to argue that there's only options 1 or 2. You get to pick 1 or 2, there's no other option, but in reality there is like a third option or a fourth option. So that's what false dilemma is about. It's like tricking you into thinking there's only really 2 options or a certain number, but really there's a secret one. And so here's the funny meme. It's like, will you press the button? You get $50,000, but the person you hate the most gets $100,000. So it's claiming that You either get the $50,000 and this happens, or nothing at all. And then the joke is that you're going to get $150,000 if you hate yourself. So that's a funny false dilemma fallacy, because what it's claiming is, again, either you get $50,000 and somebody else gets more, or you get no money at all. But there's that third option if you secretly hate yourself, I guess. So that's funny. That's a false dilemma.
Yeah. Question about setting that up. So the will you press the button screenshot, that's the false dilemma fallacy, and then the free real estate panel is a counter to the fallacy.
I don't actually know what the free real estate means. That could just be where.
Part of an Adult Swim skit when they were trying to advertise a house to a specific person for free.
Oh, nice. So no, I'm just taking these words up here as the fallacy. I have no clue what the "is free real estate" means. Is that your question?
Yeah.
Okay. Yeah. I'll have to look into this meme further. If there's lore to it. But that's false dilemma. Do we all at least understand why these ideas up here in the black make sense as a false dilemma? All right. I'll try and zoom in here. Another one, straw man fallacy. That is putting words in somebody's mouth. It's like you say one thing and you try and it's when somebody is trying to bash down somebody else's argument and they frame it in the wrong way. They knock down somebody's argument in a certain way, but it really wasn't what they were talking about. They're like putting words in that other person's mouth and they're arguing against something that they never even said. So that's what straw man is. And here's a silly example for that back in the early days of COVID. So it was like coronavirus, Austria bans all gatherings of more than 5 people. And so families of 6 have to kill off one member or something. So that is the straw man fallacy there. It's like what it's claiming is like, obviously this ban in Austria is a bad idea. Even families must be separated. And obviously that, if you go and look at the bill, it was never saying that. It was just like gatherings of 5 non-household members, people from separate households, things like that. And so do you see how that's a straw man? It's like, if somebody were to say this, that would be incorrect, right? And I guess that's essentially what the meme is saying. It's putting words into the Austria lawmakers' mouths. And that's not what they wanted. They're just trying to ban gatherings of non-household members. That's what they're trying to do. They're not trying to make you kill off one of your family members. So that's an example of a straw man. Good with that one. And of course, there's plenty more. I'm just giving you 3 examples. There's plenty more, and I want you to go back to them. But here are a couple. So the last one is tu quoque, which is Latin for you too. It's when somebody turns back an argument against them, like usually they're being criticized, and the person who is being criticized spits back at the person who's criticizing, saying, "Well, you did this thing too. Why is this a problem for me?" When in reality, of course, it was probably a problem for that person originally as well. They're just trying to help the other person out or something. So it's when you're trying to throw back an argument at somebody because they did the same thing back in the day. But that's not a problem. You were both wrong for doing it, right? So that's the fallacy. And so on the internet, of course, this phrase, "know you," is pretty much exactly that. Like, no, you did that too. Okay. And that is my last example of fallacies. Go back to the other slides and back to your essay if you'd like to see more. Are there any questions about these before I switch gears to Python mode? So I want to give you a lot of Python examples because I will be asking you coding questions on the final. Quite a few of them. All right, if we're happy, I'm going to open up idle so that we can have it ready. And then I'll figure out what lecture it is and all that. But let's see here. But before we get there, I have made you all a beautiful cheat sheet for the final because there are a lot of Python concepts that we talked about, and so I made you a cute little cheat sheet to keep them all in your head and consult them, in addition to all the other things that you're allowed to consult on the final. So I will open up the lecture notes Canvas page for today. It's not ready yet, of course. It still needs to be filled in. Like, this link is last semester's recording. The code is not uploaded yet, and I'm not going to give you the slides until the end. But there is this little CSCI 1 final cheat sheet button that you can click now. And that one works. And you can look at it. Here it is. It's a nice color-coded page that I worked very hard on to make for you, talking about conditionals in Python, how they work, if by itself, if else, if else. Just very nice with guides and arrows and colors, stuff about loops, stuff about functions. Those are the three big things, just trying to understand how they work. So you're welcome for that. Please use it. And without any further ado, let's talk about Python. Let's see here. Let's just have a bunch of examples of things, and we'll go from there. So yeah, let's talk about the original basic stuff. Once we got to Python, what did we learn? What did we figure out? Let's see here. We have types first, I guess is a good idea to talk about. So everything that you make in Python has a specific type. Like if you type a number and put that into a variable, for example, like x equals 42, that makes a box called x that you can reference that 42 with. It gets it out of the box. But the thing inside is an int. And int is a type. It's like a little cloud. And it's filled with whole numbers. Ints are whole numbers. So like you have 0, 1, 42. Negative numbers work too, negative 55, and so on and so forth. But no decimal places. That's what ints are all about. And so let's just, I don't know. Let's see how much we can get done here. Let me make a new file for all this. Save it in a place that is useful. So this is lecture 30, I guess. Did I number these right? Yeah. So this is lecture 30. Let me save that in the right spot. I'll call this Python stuff.py. Alright, so I don't know. Let's make that variable x. So x equals 42. Wrong language. You can say print. Print is a function that like takes that thing and sends it to the screen and prints it. But you can also ask for the type of something. So print the type of x, please. So this function call gets replaced with the type of x, and we're printing that now. So we'll see 42 and then int right after. So if I run this, exactly what we expect. 42, and then it's like, yeah, that was an int. So Python knows what things types are, and yeah, you can do stuff to ints. Like, what can you do to an int? You can do math stuff. It's a number. So you can print, I don't know, x plus 2. You can print x times 2. You can print x squared. Star means to the power of. And you got all these. If you print with commas, space separates the things that you put between the commas. So those are those answers there. Yeah, so you can do math stuff to ints. That's what ints know how to do. The next type was floats. Those are numbers that can optionally include a decimal place. So that's good. Floats are another cloud, but they hold all the numbers that ints hold as well as numbers with decimal places. So let's make a y variable, 3.14. And what that does, again, anytime you put that equal sign, that's an assignment of a variable to a value, and that makes this y variable hold 3.14. And we got it. It's in a box. We can ask for it. We can print it out, and we can see its type as well. Print y, print the type of y. So now we'll see 3.14, and then float, because that one has decimal places. So you can do the same math stuff to floats, but they're going to retain those decimal places. That's important to remember. A very simple type is bool, that is used for Boolean values. There's only two things in that type. It's a very small cloud. The bool type is made up of true and false, capital T and capital F. That just tells you that's like the yes. True is the yes of Python. False is the no of Python. And you can combine those, of course, with like your logical operators that we know and love, the and, the or, the not, all of those things that we remember. And you can create true and false from comparisons as well. So it's like I can make a B1 variable and set it to the result of, hey, is 33 less than 34? You see how that will become true or false? It's definitely going to become true because 33 is less than 34. So this line is just a fancy way. 33 less than 34, that's a fancy way of writing true. Yeah. And then you can, of course, assign straight like false to something, true or false. You can go like that. So print B1, print B2. We see those values as we would expect. And then you can combine them. Like what is B1 ANDed with B2? Well, if one's false, it's going to make the whole thing false. So that will be false. And then print B1 or B2. That's going to be true because one side is true, and so it's inclusive, or it takes a true if any of them are true. Okay, so that's Booleans. Please yell at me at any point if any of this is confusing or you'd like more examples. This is all for you, remember. Next, we had stir. We made strings, and so strings are, you can think of it as like strings of characters. That's what it means, like on a friendship bracelet or something. And stir is useful to learn because it lets you use the same operators as numbers in a different way, and it shows you the importance of types. So we also use it to print stuff, of course, but if nothing else, it shows us the power of types. So I can make an S variable, S1, store hello world. Strings in Python could be either single quotes or double quotes, doesn't care. And let me move this up. What is the type of S1? It is a stir. There it is. And what can I do to a stir? I can do the same operators that I was doing with numbers, like S1. I can add to it. I can add to it another string with a bunch of exclamation points, extra exclamation points. And that combines strings into a bigger string rather than making a number out of the deal. So plus could take two numbers or two floats, two ints or two floats. It could also take two strings and do a different string-like thing. S1 times 3, that's another operation. You can multiply a string by an int, and it will duplicate that string. It will replicate it a bunch of times, which is cool. Strings also know how big they are. You can ask with some work, they know how big they are. You can use the len function to figure out how long is this string, and apparently there's 13 characters in it. So that's what you can do, some things that you can do to a string, but you can use those same operators and the types matter. Get the length with len moment, right? Hopefully that's coming back to us. Next we had lists, and lists are kind of a generalization of strings. Strings are a list of characters. Lists are a bunch of anything. Could be a bunch of numbers, a bunch of floats. Could be a bunch of different types all jumbled together as well. So if I say this line, L equals that makes a big, long, size 4 list in memory that is accessible by indices. So this L becomes 2, 4, 6, 8. And the ways to get there is by the indices that start at 0, 0, 1, 2, and 3. So the index of the 6 is 2. And you can go there. You can go somewhere in a list with those indexing operations. Let me show you some of that. So here is, where's the code? There it is. So let's make a list. L1 equals 5, 6, 7, 8, 9. And then I can print the whole thing. Or I can print a part of it, like print the element at index 2, which is going to be the 7 for this example list. Because it's 0 is the 5, 1 is the 6, 2 is the 7. That's one way to do it. And you can use that same syntax to reset a value. So like instead of 7, make it 77. And now if I print L1 again, that will change the thing there. So now it goes 5, 6, 77. What else? Lists know their length as well. They're like a generalization of strings, so it makes sense. Print the len of L1, and that will give us the size of that list, which has 5 elements, it seems. So we'll get 5 there. And let's see what else. You can again use the plus they're overloaded for lists as well. So if I make an L2 list, 1, 2, 3, 4, I can add those lists together and print that out. Like print L2 plus L1. I'll just shove all those elements right next to one another and make a bigger list of a larger size. And so those are some of the things that you can do to a list of numbers using indices, just using the whole list. There's also a secret set of alternate indices that start backwards. So like if you want the last thing and you don't want to like figure out the length, you can say -1 to immediately get the last element of your list. -2 gives you the second to last, -3, -4. So there's secretly a second index that's negative for the same place in your list if you want to go that way, which is sometimes useful for going in reverse, things like that. So yeah, but the normal indices start at 0 for lists. We good with all that still? Any questions? Just a rapid fire starting Python stuff. The last thing on this slide is input. So input is a very powerful function. It's a way to get information from the user, and input takes as an argument, it takes the prompt that you want to show the user as they're typing whatever you're asking for. And then input returns a string of whatever they typed. So remember that you get a string back, because if you want to do number stuff with that string, you better convert it to a number. So I can say input, and then I give a prompt like, what is your favorite number? Something like that. And give a little space because they're going to type right after this. Close off the string, and then input's going to return the string that the user types. So I can say num and store it there, and so that'll hold whatever the user typed. Then I can print it back out, and then I can also print its type num. So, for example, if my favorite number is 42, hit enter. It's like, all right, it got the 42, it prints it out, but that 42 is in string form. It's just taking the characters that the user typed, putting it into a string. It doesn't know if it was a number or not. I could just as easily have typed, I don't know, 42. See, it's taking characters. It's a string. It's got to be a string for that reason. But that means if you want to do math stuff with it, like print the number times 2, you better be careful. You better convert first. Like if you take 42, the string, multiply it by 2, it's going to output 4242, which is not what you wanted. You would like to convert it instead. So num, replace it with the int form of num. That's what you do. You call that type that you want as like a function. So now num is an int, and then it's good. Now the type of num is what we want. It's an int. We converted it. And then if you print num times 2 now, it's going to do the actual mathematical operation that you wanted to have happen. So there it goes. Now it's an int, and you can get the 84 that you cared about, or whatever the number was times 2. Okay. So remember to convert when you're using input. Very important. Any questions about any of that? That is our first example file of the day. All right. Next example. Let's do if, elif, else. So we would like programs that can do one thing or another, depending on some conditions. And so if, elif, else gives us conditionals in Python. It lets us compare things and do one thing or another depending on the result of the comparison, whether or not it was true or false. You like check for equality, disequality, less than or equal to. There's plenty more. But the goal of comparisons is so that they allow you to like check, hey, is x less than y? If that's a true thing, if that's true, then do thing 1. Otherwise, if it's false, do thing 2. That's the whole point of comparisons and of branching, which is what this is all about. And so if you consult the cute little page that I talked about conditionals on, you can see all your options. You can control a program with a condition, like it'll either do the body or it won't, if it works like this. So here's what if statements are all about. It's like you have some code before, you say if condition, and colon, tab over, type of body, and then there's stuff after the if as well. So the way that this code executes now, if you write it like that, it's going to run, of course, the before code, and then the very first thing the if does to execute this whole thing is check the condition. If it's true, it runs the entirety of the body, and then it's like done with the whole thing. thing and then it goes to after. But if that condition was false, it skips the body. That's the whole point of that if statement. It goes straight to the after, and we're done. All right, so the syntax is always, you say if, and then you put your condition here, whatever it may be, something that's going to become true or false, because that's going to determine the outcome of things. Put your condition there, and I made way too big of a box for no good reason. So there's your condition. And then you put a colon, and then you put your body after you tab over it. Idle should do it for you. That's a tab. And then you write your body. It can be as many lines as you need, as long as it's at the same indentation level. That's the whole point of if statements. And sometimes you want to do other things. Like if it was true, do one thing. If it was false, do another thing. That's where the if-else comes into play. If the condition is true, it runs the body of the if. If it's false, it runs the body of the else. And then it comes back together. So it's only one or the other. It's always one or the other. It picks which one to do. And usually, if you have more general conditions that you want to check, it's like just like do something depending on the first condition that's true. Otherwise, do the else. That's what elif is good for. So this is if, elif, else, and you can have as many elifs as you need. But here's kind of how it works. It just finds the first condition that's true, and it runs that one and only that one's body, and then it skips everybody else, and it's done. So it's like, if condition 1 is true, that's the first thing it tried. If that's true, then run the body of the if, and we're done. Like, go straight to the end. That's the whole if, else. Just finds the first one. So otherwise, if that was false, now we have more to try. Like, all right, if that one didn't work, try condition 2. If that one's true, then do this one. Do the body of the elif. And then skip everybody else, because we just find the first one that works, and we do it. And we do it. Then finally, if none of those work, if none of your elifs work, it's always false, false, false. They're all false, and you have an else. It goes to the else. It's like, all right, I give up. Nobody else worked. I'm going to run this one. And then it's done. It's done with the whole thing at that point. So it's always this whole thing. You think of it as a chunk, and it finds the first condition that works, runs its body. Otherwise, it goes straight to the else. Otherwise, it eventually gets to the else, I guess is the right way to say it. So that's how that works. This is coming back to us. So I have some examples for this. But the whole point of elif and these else's and things is like condition. If that one's true, do this. It's all about otherwise. Elif is like the programmatic equivalent of the word otherwise. It's like if that's false, all right, try this one. If that's true, then do it. Do this thing over here. Otherwise, if that's false, then we have a bunch of other things to try. Just keep trying something until it works. Right? So here are some examples of that. Let's call this conditional step. So let's make a program that I don't know, pretends you're at an amusement park and it asks the user it says you must be this tall to ride the ride, and we'll make sure that they're the right size, they're the right height. So I'll make a new file called conditionals.py, and all right. Show you my example at the same time. Cool. All right, so you must be this tall to ride. So let's ask the user first. We need their height before we do anything. Ask the user for their height. And so we're going to need a height variable. Height. Set it to whatever the user gives us. So like input, enter your height in inches or something. Colon space. Give them some space to enter this. And then remember, we're probably going to compare this to a number. So this input that we get back is a string. It always gives you a string back. So if we want to use it like a number, let's use it. Let's get an int back. Assuming we only ever get whole number inches. If you're expecting to get half an inch by somebody, like I'm 57.5 inches, then you want to float. All right. So let's assume we get whole inches though. And now we have that height. We can compare it. Like, all right, maybe you have to be 4 feet tall to ride the ride or something. So if your height is less than 48 inches, then print, sorry, you can't go on the ride. Sad face. Okay. Otherwise, we can tell them you can go on it. Print. And remember that strings could be single quotes or double quotes. You can go on the ride. Happy face. So this is a comparison. Oops, what have I done wrong? No, sorry. Have to be consistent here. So enter your height in inches. If you are, I don't know, if you are 60 inches tall, then it's like, yeah, you can go on the right because your height less than 48. It's like, is 60 less than 48? That is false. So it hits the else. And if we run into this again and pretend we are small, if I am, I don't know, 42 inches tall, then it's going to say true because 42 is less than 48, and it will print, sorry, you can't go on the ride, and that is the end of the if else. Any questions about that example, how it's working? Picking one or the other? That's a good one to study, I think. Another example is a grade calculator. Let's do that one. So you can have as many LFs as you want, by the way. So here's an example of using just one LF, but you can have LF condition 3, LF condition 4, LF condition 5 right after this, and it just keeps trying them. Just keeps trying them. So let's do a grade calculator for A, B, C, D, and F. That was a good example of this, I think. And so let's ask the user for their grade now as like a percentage. So let's store that grade equals input, enter your grade as a percentage, colon space. And percentages can totally have decimal points because it's just take the points in the class and divide it by the maximum. So this could totally be a float. So you'd have like a 92.5 or something. So we want to get that back and keep the decimal places. So we'll convert it to a float number type. And then now it's all about, all right, what grade did you get? A standard way of doing that is like, see if it's an A and print if it's an A. If it's not an A, then all right, see if it's a B. If it's not a B, all right, see if it's a C. And do it in that order because that helps, especially if there's extra credit. That's the right order. So if your grade, for example, is greater than or equal to 90.0, or just 90, whatever you want to say, then it's an A, right? It's a 90 or above, then we know this grade must be an A. Print A, we're done with it. Elif, all right, if we weren't greater than or equal to 90, and we got here to try this next condition, that means we must have been smaller than 90. You see that? So everything, now we know that the grade is less than 90. And so we can check for the next thing. So if it's less than 90 we got here, all right, how about what if it's bigger than or equal to 80? If that's true, it's a B. And it'll never be wrong. It's like this is the proper order for this. Because if we ever get to the try this condition, that means the first one must have failed. Because it's only ever going to do the first one that works. All right, if it's greater than or equal to 80, then we print a B. And that makes sense. Elif, right, we have to check for C now. Because if that wasn't true, go and try the next one. And what does that imply? If this was false, what does that imply? It implies that grade was less than 80. So it was a C or worse. So let's try C next. And this is a good order. So LF grade is greater than or equal to 70. If that's true, then it's a C. And I think you see the pattern now. Oops, print C. Otherwise, if it wasn't a C, maybe it was greater than or equal to 60 still, and that was a D. Otherwise, if none of that was true, then what is true? So if this is false still, this condition still doesn't work, that means the grade must have been less than 60. And anything less than 60 on normal grades is an F. So we can call that an F. And that can be our else. Nothing left to check. It's just like if the one from before still didn't work, then let's call it an F. And that is all. And so this will work. I don't know, 42. Grade as a percentage, I don't know, 92. A. 72. That's a C because, like, all right, it's not greater than or equal to 90. 72 is not greater than or equal to 80, but it is greater than or equal to 70. That's the first one that works. It's going to print C. And then finally, I don't know, 55. F because it fails all these. False. 55 is not greater than or equal to 80, not greater than or equal to 70 or 60. So it hits this one and it says F. All right. Any questions about this example? Very long chain of if and else. Okay. I guess it's loop time. So the first loop that we talked about was a while loop. That's probably the conceptually easier one to kind of understand. It's the most generic kind of loop. And a while loop is all about taking a condition and repeating some code as long as that condition is true. So a while loop is very simple. It's like, while this condition is true, it looks just like an if, then run the body. So it's like, it runs exactly as you would expect. It like goes, first thing it does is check the condition. If it's true, it runs the body, and then it jumps right back to check the condition again. As long as that is true, as long as this condition is true, it's going to keep looping and run the body. Run the body, run the body, until the condition becomes false, eventually, or maybe immediately, who knows. Then it's done with the whole loop the second the condition becomes false, and it goes and runs the rest of the code. Okay? That's how a while loop works. And let's have an example. So, how about one example? We could let's print all the numbers from 1 to 10. And here's kind of how you want to think about it. You think of it as a looping program, and this can be very easily translated to a while loop. So, like, the first number you want to print is 1, and you want to keep printing as long as that I that holds the number you're about to print is less than or equal to 10. So that's the first thing that we check. As long as that's true, if that's true, then we print I, and increment I as well, so that we print 2 next and 3 after that, increment I. And then we jump back to check the condition, because like 2, 3, 4, they're all going to get printed. It's going to stay true. I is still less than or equal to 10. But the second I is 11, this comparison is false, and that's when we want to stop. That's when we want to like continue with the rest of our code. No more loop. So if that's false, we'll do the after stuff. So that's how you can do that kind of loop, and that translates pretty quickly to a while loop. Loop stop. So let's translate that. So, all right, I'm just read it off really. I start at 1. While I is less than or equal to 10. What do I want to do? I want to print my I want to increment my I equals I plus 1. And that's pretty much it. Run. There it goes, printing from 1 to 10. Do we see how this code prints from 1 to 10? Does it make enough sense? You can print in reverse. You can do I equals I minus 1. All those fun things happen. One thing I don't think I showed you yet is if you would ever like to stop a loop early, or you'd like to stop an infinite loop on some condition, you can use the break keyword in Python. That stops a loop, whatever loop you're inside of early. So, like, say we hate the number 8 and we don't want to go to print that one. So, like, if I is equal to 8, you can use the break keyword to stop early. That'll just stop the loop. So, stop early with break. You just say it on a line by itself. And this will stop it at 7, because the second we like print the 7, make I 8, then once we say this, it's true now, and that breaks us out of the loop. That's how you say it. You broke out of the loop. And so that lets us stop early, even though we may have continued further if that break was not there. So that's a fun, useful thing that you might want to use sometimes. Let's see, another example. A good example of needing break. One way you could use break is in the second example, but I'll show you an alternate way. Let's make a program that sums all the numbers that the user types. Like they're just typing a bunch of numbers, and we want to give them the sum, and we know that they're at the last number and they want the answer when they type -1. We're not going to consider -1 to be a normal number to add. These are just going to give us a bunch of numbers like this, and we'll add them all up. And then once they type -1, we're going to stop our adding loop. We won't add anymore, then it's time to give back the answer. Right? So the -1 signals that the user's done typing things. That's how we know. So if the user types these numbers, then we should output the sum of those ones before the -1. The -1 just does the stopping. Let's see here. So let's do that example. Here's the idea over here. So what does that mean? Well, we need to keep track of like what's going on. We need to add a bunch of numbers into something, so let's start a variable for that. Keep track of the sum in a variable. So I'll call it like total. Starts at 0, of course. And then we want to keep getting new numbers from the user, and we got to get the first one definitely. So like, let's call it next num equals, let's ask the user to enter the next number, or -1, to stop us. Colon space, so that gets us the first number. And we want it as a number as well. Like right now it's just a string, so let's make sure it's a number, an int. There we go. And so we got the number, and what we want to do is keep on like adding that number that we just got while it's not equal to -1, because -1 stops us. It's like, I'm done typing things now. So while next num is not -1, because the second it is, we want to stop. So while it's not -1, what do we want to do? Well, we just got a number from the user. We would like to add it into the total. So we're trying to keep track of the sum here. And then we want to ask for the next number. This input line is outside of the loop. There's a cleaner way to do this with a break. I encourage you to think of it. But we want to get the next number, and so we want to repeat that idea as well. So let's get the next number inside the loop. It'll just be a copy of that previous line outside. So those are the two things we got to do inside this loop. Add next num into total, so that one counts, because it was a -1. And then we want to get the next number. So that's just this all over again. Ask the user for another number, because maybe now it's -1, and we want to stop. See that? That is a possibility. Definitely. Oops. So, what does this mean? If we get down here, like we get to this code down here, and we stop the loop, what's true? Right? So when we get here, it must have been the case that this condition was false. You see that? This must have been false, because otherwise, if it was true, we would have continued the loop. We stopped the loop if we ever got here, which means that next num must have been 1, because it must have not been not equal to 1 is how you think about it. So when we get here, next num, the only way that we could have gotten here out of the loop must have been next num becoming -1. And that means that we want to see the sum now. So our job now for the rest of the program is to output the sum, and that lives in the total variable. Okay? And we can make it cute. We can be like, the sum is colon space, or a comma to do the spacing. But that is the code. That's the idea. So enter the next number. I don't know, 1, 2, 3, 4, 5, -1. And so that'll add all the numbers from 1 to 5. Does that make enough sense? If you just type -1 immediately, then the sum is 0, because you gave 0 real numbers. But it's still going to work. What's the sum of 5, 6, and 7? Or 4, 5, and 6, I guess. Sorry. That is also 15, apparently. Cool. Are there any questions about why this code is going to add up a bunch of numbers? We keep on asking for numbers until we see -1. Don't forget to convert those types, though. Alright, for the last thing I want to do today, let's talk about for loops. Those were a way of going through something, and that something is, I want you to think of it as a list. Slightly more generic, but that's good enough for this class. So a for loop, it iterates through something, like a list. So you have a list 1, 2, 3. If you want to like do stuff with every number, a for loop will go at every number and get it for you, and you can use it. Range also makes a list kind of thing. So like if you say range of 50, that's pretty much making a list for you. It's making a list that starts at 0, 1, 2, all the way to 49, because it's weird like that. It goes not right up next to the number that you give, but not equal to it. So that's what that does, the range. Let's see, what do I want to show you there? Well, I can show you this code first. Here's a for loop. What it does is like for, you give a variable name in some sort of list-like thing, like a range or a real list, and that variable gets the next value of the list. What happens is, as long as there's another element to look at, it gets put into that variable name that you supplied, and it runs the body of your loop. So it's like, is there another element in your list? Yes. It sets the variable to that next element. the first one at the beginning, of course. And then it runs the body, and then it keeps on coming back here as long as there's another element in the list. The variable gets set to that one, and it runs the body. Eventually, once you've exhausted the list, there's nothing left to look at, and so then at that point you're done with the loop. All right, so let's see what I want to show. I just proved to you that range really makes like a list. So like range of 10. If you press enter, like it's its own little thing, but you can convert it to a list. Oops, gotta close it off. And so that's 0 through 9. Range can take 2 arguments as well. List range, like 1 to 10. That's like gives your starting value. So this one is inclusive, but the last one is exclusive. It goes right up to that one, but not including it. But it includes the first value. That's range. Let's see here. What do I want to do? So let's make a fancy example. It's going to take some typing. So let's make an example that gets a bunch of numbers from the user. So the user is going to enter a bunch of numbers. We're going to put them into a list. Then we're going to find the minimum number inside of that list. Okay, that's going to be our goal. We're going to get a bunch of numbers from the user, put them into a list, and then find the minimum of that number. All right, and I'll remind you of the algorithm once we have that list. So let's get the list first. That will involve a while loop, but then we'll go to a for loop to go through the list once we've made it. So this is for loops pi, and so let's get a bunch of numbers from the user so that we can go through them in a fancy loop and find the minimum value. So let's call that list of numbers L, and we'll start it off empty because we haven't gotten anything from the user yet. And our goal is to fill L with numbers that the user enters. And maybe we'll have them enter a bunch of numbers, and then -1 is when they say we're done. Like -1 is the special value. So let's just steal that code. Let's steal all this code all over again and use that to fill this list L. Let's get the next num. I guess I have to make this bigger. Let's get that next num. And as long as it's not -1, let's add it into L. So L equals itself plus that new number at the end. So just give it make it as part of a brand new list. So it'll combine these into a bigger list with next num at the very end. So that's how you do it. And then get the next one until it's -1. And at that point, once this is done, once we type -1, then we filled L with everything we wanted to put in it. And so now it has actual values. So like 1, 2, 3, -1. That put all those into L, and so L is 1, 2, 3, and it can be whatever you want. 9, 8, 42, 51. All those numbers. So that's how you fill the list. That's a while loop. Any questions about that? It's similar to our previous example. Because now we're ready to find the minimum of all the numbers in the list. So let me remind you of that algorithm. So the way that minimum finding works is you have a variable that's eventually going to hold the real minimum. Like let's start it. Let's make it. And then you have your list. Like maybe the list was 3, 1, 2. And the algorithm for the minimum is you start with a guess. You make a guess for your minimum. You guess that it's the very first element of your list. Because like it could be anywhere. Maybe it is the first element. Who knows? For this example, it won't be. But that's the first guess for your minimum. And you're going to store it in your min variable. And then you're going to go through the rest of the list and check and see, was that a good guess? Maybe it wasn't, and you'll want to make a better guess as you see better values. So you loop through the list, updating your guess as you see something smaller. So like you saw the 3, now you see the 1, you compare that to what's here, it's smaller, so it's a better guess for the true minimum. And so you replace it. Replace the min variable with that smaller thing. And then you look at the next thing. Like, all right, I see a 2. How does that compare to the 1 that I'm guessing is the minimum? Well, it's bigger, so 1 is still a good guess. I haven't found something smaller, so I'll keep my 1 there. I won't replace it with 2 or anything. And then, by the time you've visited everybody, you've given them all a chance to win out for the minimum. And you will have found the true smallest thing by the end, once you've visited everybody. Does that make sense? That's the algorithm, and we can print that. Or we can implement that and then print out the minimum. So it's just loop through the list, update your guess every time, and then once you're done visiting everybody, just by construction, you must have the true minimum, because you kept replacing with the smaller thing, and you will eventually have replaced with the smallest thing, and it's never going to get replaced anymore. That's minimum finding. So, all right, make a guess. That's step one. Make a guess that the min is the first element of the list, L. So make a guess that we're going to save it in a min variable. Make a guess that it is the first element of this list, which is L of 0. Okay? Then loop through every other element. But let's just go through the list again. It just won't get replaced the first time. Loop through every element of L and update our guess. So this is how you use the for loop. You say for, give a name of a variable like x, and then you say in L. So for x and L, what this does is it goes through L and it lets x have a chance at being every element in order. So, all right, x is the next element of L. We're going to try them all in the for loop. And so our algorithm goes, if, we got to check, if x is a better guess for the minimum, then min should be set to x. That involves an if. So if x, the value in the list that I'm currently looking at, it's a better guess for min, which means it's smaller than my current guess for min, then I better replace min with x. Put the smaller value in there because it's a better guess. See that? And then once this loop completes, we'll just keep on replacing it. If we ever find something smaller, eventually we will have found the smallest thing, and then it never gets updated. It never gets replaced after that. So now, once we're done with the list, min must hold the true minimum. So print. What is the min? It's whatever the min variable holds. So we do the 3, 1, 2, -1, then the min is 1. It figures it out. Like 3 is the first guess, but 1 is the better guess, and 2 is 2 doesn't help. 2 is not better than 1. And it'll find it regardless of where it is. Even if the first number is the minimum, it'll figure that out. Notice like the first guess never gets replaced. Or if it's the very last thing, it doesn't care. It'll eventually find it, and it's smaller, so it's going to replace it. The minimum will always eventually be the correct thing as long as you try them all. All right? Any questions about why this code, why this algorithm works? Or the for loop syntax, any of that? It goes through the entire list, lets x have a chance at being every element in order. Let's see here. Another cool example that we did in our logic slides was we used code to prove that a proposition was true. So here's a proposition. We can prove it to be true. Prove that there exists an x that is between 32 and 37 and it's prime. Prove, that's essentially claiming that there is a prime number between 32 and 37 inclusive. You see how I'm reading that? Hopefully these symbols are still fresh in your mind. But this is something we can go and prove. It's like, all right, if this is true, we could just search between 32 and 37 the second we find a prime number. If we find one, then that's proof. That could be our x. Like maybe it's 33 or something. I don't know. I don't think 33 is prime though. No, it's a multiple of 3. But maybe there is a number between here and here that's prime. If there is one, then that's a true statement, right? So that we can use a loop to go through this range looking for a prime number. And if we find one, that means we have proven our proposition true, which is cool. So let's do that. Let's see here. So essentially, we just want to search for every number n in the range between 32 and 37. So we have to say range 32, 38, so that goes up to 37, because range in Python is weird. So this will iterate from 32 to 37. What do I want to do with n? Well, n is another number. It's the next number. It's like first is 32, then it's 33, all the way to 37. I want to check if that number is prime. If it is prime, then we found a proof. We found a value that x could take on that proves our proposition. Proves it true. So if n is prime, like, well, maybe we'll have an is prime function. If is prime of n is true, then that means we found a number within the proper range that is prime. We've proven our statement. Print the statement is true! Exclamation point. You can break out of the loop now because you don't need to do anything else. But we'll just keep on going. And we'll print that x, n, whatever it was, that's the thing that was prime. There. So, are there any questions of how this code will disprove this predicate? Not predicate, sorry, proposition. We'll prove it to be true or false. Prove or disprove it. Because if it doesn't print anything, that means it didn't find anything. That means there is no good value for x that is prime between that range. But if it does print something, then it did find something, and that is our value. So it's just asking, hey, does there exist an x such that this is true for it? Yeah, we found one good one if this returns something. And so we need is prime function. I will just implement that quickly. This is not part of the something I care about you learning, but here's how you can check if a number is prime. Let's just make a quick function. What you do is you see if that number has any factors besides 1 in itself. So like try every other possible factor for n in range between 2 and the number minus 1. Secretly, you're just looking for one factor, so it could be the square root. You can go up to the square root of the number. That makes it better. Better algorithms like number to the 0.5 power. That's the square root plus 1. Again, it doesn't really matter. We should make this an int though. So we need something for our range. So go up to that and see if you find a factor. And so n is a possible factor. See if it works. So see if num, if you try to divide it by n, if it goes in cleanly, there's no remainder, nothing left over, then that means we found a factor and the number is not prime. Return false. Otherwise, if you tried every possible value, you're looking for a factor and you didn't find any, you never returned false. You stop this loop, having tried everything, and well, you found no counterexample, so it must have been a prime number. And so that is the code. And I don't know, 1, 2, 3, that's the minimum stuff. And then it runs our code, and it's like, the statement is true because 37 is a prime number between 32 and 37. It worked. It found one. And so that is code that proves or disproves a hypothesis. Proves or disproves a proposition, which is fun. Any questions about that? Where's the code? There it is. All right. That's where I want to stop today. We will do more next time. And then I'll give you all the rest of the stuff. Let's see. Yeah, it's just the lecture today.